Okay, continuing with the formation of ionic compounds. Binary ionic compounds, compounds that involve two elements like sodium chloride, will involve a metal and a nonmetal. As we've said before, the metal loses some valence electrons to form a cation. The nonmetal gains some valence electrons to form an anion, and then the attraction between the positive and negative ions is the ionic bond itself. That's what keeps the compound together. The electrons, it's important to remember, though, that the electrons are transferred directly from the metal to the nonmetal. And that's the metal is not going to release any electrons until there's something else there that's willing to take them in. You don't just find free electrons floating around in solution. They have to belong to an atom or an ion or a molecule or something like that. So the transfer of electrons is not actually going to happen until the metal and the nonmetal are right there next to each other. The main group metals form ions by losing their whole valence shell, and that gives you the electron configuration of the last previous noble gas in the periodic table. And that's a great deal of stabilization that comes in from that. And nonmetals form anions by gaining enough electrons to reach the same electron configuration as the next noble gas. So like when we have something like nitrogen, we can tell that nitrogen is normally, it's going to want to gain 3 electrons because that's how many electrons it has to gain to have 10 electrons like neon does. And so -3 would be the most likely charge for nitrogen to take as an ion, at least. Let's see. So the relative numbers of cations and anions involved in the formula for an ionic compounds depends on the ionic charges on the cation and anion, and that in turn depends on how many electrons were lost by the cation versus how many are gained by each atom of the anion. And because the total overall charge on the formula for the compound has to be 0. So for a compound has no electrical charge by definition. And so the total negative charge or total positive charges on the cations has to equal the total negative charge on the anions. For something like sodium chloride, it's really easy. A sodium atom releases 1 electron to become a sodium plus ion, and that 1 ion is taken in by a chlorine atom to become the Cl minus ion. And Na plus and Cl minus will then go together in a 1-to-1 ratio for NaCl. With something like calcium, calcium is in group 2A of the periodic table, so we know right away it's going to lose both of its valence electrons and have a +2 charge and release 2 electrons. But if you're talking about something like calcium chloride, each chlorine can only take in 1 electron before it's stable and has a noble gas configuration. So it's going to require 2 chlorines, which will each take in 1 electron. So the 2 chlorines are taking in 2 electrons and becoming 2 Cl minuses. You can see I've put parentheses around the reaction to show that the 2 applies to everything inside the parentheses. And you get the formula CaCl2. The total charge on the cation is +2. The total charge on the anion part of the molecule is -2 because you've got 2 chlorides at -1 each for -2, and +2 minus 2 adds up to 0. Something really fun like aluminum oxide, you've got aluminum, which will lose all 3 of its valence electrons to become Al +3 and release 3 electrons. Oxygen, though, needs to gain only 2 electrons to reach a noble gas configuration. So each oxygen will take in 2 electrons to become the oxide ion, O2 minus. And we've got a mismatch here. We've got Ao +3 and O2 minus. The goal here is to get the number of electrons to be the same. The only thing you can do with 2 and 3 to get them to be the same is multiply the 3 by 2 and multiply the 2 by 3. So if we multiply this entire top reaction by 2, we get 2 aluminums going to 2 Al plus 3s and 6 electrons. And if we multiply the entire bottom reaction by 3, we get 3 oxygen atoms taking in 6 electrons to become 3 oxide ions. 6 and 6 would be the same for the electrons, and so the formula for the compound is Al2O3. Oops. And you can check that because the total positive charge for the cation part of the molecule and the total negative charge for the anion part of the molecule have to cancel each other out. If you've got 2 aluminum ions at +3 each, 2 times 3 is +6. We've got 3 oxide ions at -2 each. 3 times -2 is -6. +6 minus 6 adds up to 0. Remember, though, that in each case, the actual compound is a 3-dimensional array of alternating positive and negative ions, and it just happens to work out that this is the overall ratio of one to the other. In figure 7.3 on page 345 or 355 will give you a pretty good representation of that. Because ionic compounds exist as 3-dimensional arrays, not as separate individual units, it's not really proper to refer to molecules of ionic compounds. We slip and do it sometimes because it's a convenient way of doing things. But for instance, NaCl should not be referred to as a molecule. That should be referred to as a formula unit instead. But we might slip and say molecule of NaCl from time to time. What we really mean is the formula unit. Also, ionic bonds are really strong, as I mentioned before. One way you can see that is if you look at the energy that's necessary to separate the ions in the lattice, the crystal array for an ionic compound. So if you take solid sodium chloride and separate it into gaseous sodium ions and gaseous chloride ions, that takes 769 kilojoules per mole in order to do that. And that's positive. That's the energy you have to put in. That's also known as the lattice energy. It's basically the energy that you need to break up the lattice of an ionic compound. And 769 kilojoules per mole is actually quite a lot of energy. That's a lot more than it takes to break the bonds in most covalent compounds, for instance. Okay, so once again, looking at the electron configuration of cations, I'm just going to go through this fairly quickly because we did this not too long ago in the last chapter. The main group metals, remember the A group metals, lose all of their valence electrons. That results in them having the same electron configuration as the last previous noble gas. All of the orbitals in the new valence shell will be completely filled, and that will make it stable. So the ions are actually more stable than the atoms for main group metals and metals in general. The group number is equal to the ion charge for A group metals. And that's because, well, the group number equals the number of electrons in the valence shell. And that's the number of electrons you're going to be missing once you form a cation. And so that's what the charge will be, that number. And it'll be positive because you've lost the electrons. And it's that only works for the A group metals, though. The B group metals are more complicated, and we'll get to those in a little while. So, for example, as we've already seen, the sodium atom has this electron configuration with 11 electrons. That's equivalent to having the same configuration as neon plus a 3s1 electron. When you lose an electron to form an Na plus ion, it's that 3s1 electron that goes, and now you have the same electron configuration as neon. So Na plus is isoelectronic with neon. Similarly, calcium 2 plus loses its valence electrons, which gives it the same electron configuration as argon. And so calcium plus 2, or calcium 2 plus, whichever you prefer to call it, is this isoelectronic with argon, which makes it much more stable. Aluminum plus 3 loses its valence shell. Here, it's important to realize that the valence shell is all of the electrons or all of the orbitals with the highest number for n. So in aluminum, the valence shell is 3s2, 3p1. That's a total of 3 electrons in the valence shell. And it loses all 3 of those electrons when it forms the Al plus 3 ion, which gives it the same electron configuration as neon. And so Al plus 3 is isoelectronic with neon. There are some exceptions with some of the metals that are near the bottom of the groups, particularly those that are adjacent to the transition elements. So for instance, lead is in group 4A. You'd expect it to have a charge in its ions of +4, but actually it's usually +2. Yeah, okay, there are exceptions to everything. Tin is in group 4A also, and it can have a charge of +4 in its ions, but it can also be +2. And thallium is in group 3A, so you'd expect it to have a charge of +3 in its ions, but it's actually more often +1. Mercury is in group 2B, and it does 2B, which makes it a transition element, so you'd expect it to be kind of weird. It does often have a charge of +2, but it also forms this weird dimer ion, Hg2 +2, where each of the Hg's each of the mercury atoms in that dimer has a charge of +1, but they're bonded to each other, and collectively they have a charge of +2. So you see that sometimes also. For the transition elements, things, like I said, have less predictable charges. Things are a little more complicated because the electron structure is more complicated. But we do know that the first electrons to be lost when a transition metal forms a cation will be from the s orbital of the highest numbered shell. They will go first. So if the transition metal has a +1 charge as an ion, it will lose one of the s electrons in the highest numbered shell. If it has a charge of +2, then it means it loses both of the s-type electrons in the highest numbered shell. And it's only if it has a charge of 3 or greater that it starts losing electrons in the d orbitals of the next shell down. Okay. And most transition elements have charges of +1 or +2 or +3 or some combination of those, although some can go higher. Some can go as high as +6 or +7 even. So iron has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6, and then 4s2, because iron is here. So it would have 4s2 and then 3d, 1, 2, 3, 4, 5, 6. Iron +2 will lose the 4s electrons first, and so it will still have the 3d6 though. And so this is the configuration for iron +2. Iron +3, though, that's when you start losing the 3d electrons. So iron +3 ends with 3d5. Iron +3 actually is encountered somewhat more often than iron +2, and that's because notice the d orbitals in the third shell are half filled. There are 5 d orbitals. In this case, each of them would have 1 electron, and that is a little bit more stable than the situation like this, where 4 of the 5 have single electrons in them, but one of them has one d orbital has a pair. So Fe +3 is a little bit more stable than Fe +2. The intertransition elements, that is the lanthanides and the actinides, these misfits down here at the bottom, they will usually have charges of +3 as cations. And that means the loss of the s electrons from the valence shell. And then you will lose 1 or more electrons from either a d or an f orbital. But we don't use those much, so we won't worry too much about those. Okay, for nonmetals now, for monatomic ions of nonmetals, the nonmetal, as we know, tends to gain valence electrons until it reaches the same electron configuration as the next noble gas in the periodic table. the number of electrons gained will just be the number of spaces you have to move between the nonmetal and the next noble gas. So for, say, phosphorus, the number of electrons gained by phosphorus would be 1, 2, 3, because that's how many spaces you have to move to get to the next noble gas. So phosphorus is going to form a -3 ion because its electrons have negative charges. So if you gain 3 electrons, that's -3 in terms of charge. And it will have 18 electrons just like argon does. And so say for nitrogen, has an electron configuration of 1s2, 2s2, 2p3, because it's the third element into the p block in n equals 2. So 2p, 1, 2, 3 will be how it ends. And then if it wants to form an ion, nitrogen, like phosphorus, is going to gain 3 electrons. So it will be 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6, just like neon. And that's what makes it so stable. Sulfur will gain 2 electrons, in which case it will have the same configuration as argon. And phosphorus, as I just said, will gain 3 electrons, so that it has the same configuration as argon. All right, this brings us to covalent bonding. So that was a summary of ionic bonding. Now we can move on to covalent bonding. Ionic bonding is a case where one ion has a much greater attraction for electrons than the other one does, or one element does. And the element that has the greater attraction for electrons will actually take electrons completely away from the other element. So in ionic compounds, it's usually the nonmetal will take electrons completely away from the metal. And that results in formation of ions, which is the result of either completely gaining or completely losing electrons. In covalent bonding, the elements involved will have more similar attractions for electrons, so that one of the elements might be able to move the electrons closer to itself and away from the other one, but the difference in attractions won't be big enough for one element to completely take the electrons away from the other one. So they have to share the electrons. And they may share them unequally, but they have to share them. And covalent bonding occurs between nonmetals. So if you have 2 nonmetals bonded together, it's going to be covalent bonding. Covalent bonding can occur between elements or atoms of the same element, like the diatomic elements, for example, H2, O2, Cl2, N2, and others. And also sulfur, which tends to be found in clusters of 6. So S6, that would involve covalent bonds. Or it can happen between different elements, like in H2O. Hydrogen and oxygen are both nonmetals. They're connected by covalent bonds. Carbon dioxide. Carbon and oxygen are both nonmetals, and they're connected by covalent bonds. Glucose, or actually any number of other sugars, have this same formula, just different arrangements of the atoms. Carbon, hydrogen, and oxygen, they're all nonmetals, and they're all connected to each other by covalent bonds. Okay, and the reason that we form covalent bonds, literally covalent means bringing your valence shells together, or in other words, sharing valence electrons. And the reason we form covalent bonds is because the electron affinities or electronegativities of nonmetals are fairly similar to each other. In the case of a nonmetal and a metal, the metal is going to have a much, much greater electron affinity or electronegativity, and it can take electrons right away from the atom or of the metal. But with nonmetals, they have fairly similar attractions for electrons, and the differences are not great enough for a complete transfer of electrons from one atom to the other. They instead have to share. And they share one or more pairs of electrons. Usually, the pair of electrons that shared, one of the electrons will come from one atom, and the other electron will come from the other atom. If the elements on either end of the bonds are the same, then the bond is considered nonpolar. So for something like hydrogen, with a hydrogen atom at either end of the bond, obviously both atoms are the same element, so they will have the same level of attraction for the electrons. And so the electrons will not be closer to one atom or the other at any given moment. They will most likely be evenly distributed between the two atoms. And so there's no positive end to the bond. There's no negative end to the bond. The charge for the bond will be the same all along because the electrons are evenly distributed. And that's known as a nonpolar bond. Also known as a pure covalent bond, just meaning that it's like pure, perfect sharing of the electrons. The book likes to call them pure covalent. I usually call it nonpolar, but they mean the same thing. So the electrons are evenly distributed between the two nuclei. But the sharing can also be unequal, and that happens whenever the elements are different from each other. So like in water, H2O, bonds between hydrogen and oxygen, the oxygen has a greater attraction for electrons. And here's where that diagram I showed before starts to make sense. The oxygen has a greater attraction for electrons than hydrogens do. And so the electrons involved in the hydrogen-oxygen bond will tend to be pulled closer to the oxygen and away from the hydrogen. And so the oxygen end of the bond will have a partial negative charge on it because the electrons spend more time up there by the oxygen. And the hydrogen end of the bond will have a partial positive charge on it because the electrons spend less time down by the hydrogen. And that'll be true for both bonds. And so the way the oxygen, or the water molecule rather, is arranged, you actually have one entire end of the molecule that has a partial negative charge on it, and one entire end of the molecule that has a partial positive charge on it. And that's why ionic compounds are so good at dissolving in water, because the negative end of the water molecule attracts positive ions, and the positive end of the water molecule attracts negative ions. But back to covalent compounds. Carbon dioxide is another example. Carbon and oxygen have different attractions for electrons. The electrons will be drawn more closely to the oxygen than they are from the carbon. And so the oxygen end of the bond will be more negative, and the carbon end of the bond will be more positive. And it's the same for all the various complicated bonds in glucose as well. So the electrons, again, are pulled closer to the end of the bond with a more electronegative atom. That'll be the end that's partial negative. And away from the end with the less electronegative atom, that'll be the partial positive end, like in the water molecule here. Sharing of valence electrons occurs as a way that both atoms can be more stable at the same time. Because the neutral atoms, as they are in the periodic table, unless they're members of the noble gas group, they have sort of non-ideal electron configurations. They want to either gain or lose electrons in order to get to the same electron configuration as one of the noble gases. If they don't have enough power, that is enough attraction for electrons to take electrons away from any other atoms in the vicinity, or if there are no other atoms in the vicinity who have enough attraction for electrons to take electrons away from the atom in question, then they can achieve that stable noble gas configuration by sharing electrons with one of the other atoms in the vicinity. And the simplest example would be hydrogen, where each hydrogen has one electron. And so I'm just using a dot to represent hydrogen's one electron, and the H represents the nucleus. So hydrogen with one electron is not very stable. Hydrogen would much rather have two electrons like helium, or no electrons at all like the H+ ion. If that hydrogen atom is in the vicinity of another hydrogen atom, well, that hydrogen atom is also unstable because it has one electron. And it would much rather have two electrons like helium also. But since they are the same element, neither one of those electrons has the power to take an electron away from the other one. But what they can do is share those electrons. So they kind of come together. Each of them contributes one electron, and they share them as a pair of electrons between the two nuclei of hydrogen. And so you can draw that like this, with like two H's with two dots between them. And the way this works, those 2 electrons now belong to both of those atoms simultaneously. So you can consider both of those electrons to belong to the hydrogen on the left, which means the hydrogen on the left effectively now has 2 electrons, just like helium, so it's stable. And they also simultaneously belong to the hydrogen on the right. So the hydrogen on the right effectively has 2 electrons, like helium, so the hydrogen on the right is now stable also. So they can get to this noble gas configuration by sharing electrons as well as gaining or losing. And they share them when they basically don't have enough power to transfer them. Properties of covalent compounds are generally sort of less extreme compared to those of ionic compounds. For one thing, covalently bonded molecules or compounds can be solid, liquids, or gases. Hydrogen, for instance, is a gas, and that's a covalent bond. Covalently bonded solids tend to be softer than ionic solids. If you think of something like, I don't know, sugar, I guess, or wax, think of something like candle wax, that's covalently bonded, and it's definitely quite a bit softer than something like salt. They have relatively low boiling points and melting points compared to ionic solids, although some of them, some covalently bonded compounds have pretty high boiling points and melting points, but they're generally lower than those of ionic solids, which are very high. Most are not soluble in water, and they are poor conductors of heat and electricity. So they're fairly different from ionic compounds. For the formation of covalent bonds, we've got basically as 2 nonmetal atoms without filled valence shells, for instance, the hydrogen on the previous page, approach each other, the potential energy decreases due to the attraction of the nuclei for the pair of valence electrons between them. And when they reach a certain distance apart from each other, the potential energy reaches a minimum. But if you try to get them any closer, then the positive charges on the nuclei of the 2 atoms start repelling each other. And so the potential energy goes back up again. And there's a diagram of figure 7.4 on page 348, 358, which shows that for the hydrogen atom. And essentially the length of the covalent bond then ends up being the distance between the nuclei when the potential energy is at its lowest point. Because again, low energy means greater stability. So we generally want low energy. And that's, if the nuclei move any closer from that point though, the potential energy starts increasing again. So the low point in potential energy, that's the most likely length for the bond. The formation of a bond always releases energy. Breaking a bond, you have to put energy in, but when you form a bond, it releases energy. Some bonds will release more energy when they're formed versus others. And these values are well known and they're tabulated. You can look them up. For hydrogen, taking 2 hydrogen atoms in the gas phase and forming a covalent bond between them will release 436 kilojoules per mole of hydrogen. So you release that energy when you form the bond. If, on the other hand, you had a mole of hydrogen molecules, H2 molecules, and you wanted to break them apart into separate atoms, you would have to put in that same amount of energy. So H2 gas going to 2H gas would be plus, the delta H would be plus 436 kilojoules per mole. Because it's the same process, just in reverse. So the energy you get out going one way is the energy you'd have to put in to go the other way. Okay, so the next topic, which we'll cover next time, will be pure covalent, that is non-polar covalent, versus polar covalent bonds. And we've already talked somewhat about the difference between them, but we'll get into more detail next time. And I guess that's it for today. So I'll see you next time.